Something arrived from outside our solar system in 2025 and it might have brought company. 3I Atlas, the third confirmed interstellar visitor, didn't just pass through quietly. It carved a path through the Oort Cloud, that frozen shell of debris encircling our sun at unimaginable distances. Now astronomers are detecting something strange. Dark objects, high inclination trajectories, arrivals that shouldn't be possible yet according to standard physics. The timing is suspicious. Atlas glows bright, impossible to miss, drawing every telescope in its direction. But what if that's the point? What if the real story isn't the comet we can see, but the invisible swarm trailing behind it? Stay until the end, because the evidence suggests we're not watching an arrival. We're watching the opening act of something far larger, and we might already be too late to look away. If you're as captivated by this cosmic puzzle as I am, go ahead and like this video and subscribe to stay with us as this story develops. Leave a comment telling me where you're watching from, what time it is in your corner of the world, and whether you think we're seeing the complete picture of what's really happening out there in the dark. Part 1, the shock opening, the 3I Atlas. Wake and the impossible timing problem. Something is arriving ahead of schedule, and nobody wants to talk about it. Right now, astronomers are tracking dozens of new objects sliding into the inner solar system. They're dark, they're quiet, they barely reflect sunlight, and some weren't spotted until they'd already crossed Mars's orbit. Officially, these are classified as near-Earth objects, part of the usual background noise of cosmic traffic. But here's the problem. Their timing doesn't make sense, not according to standard models, not according to the slow-turning machinery of celestial mechanics that's supposed to govern how things move out there in the cold. Because if something disturbed the Oort Cloud years ago, a distant shell of icy debris encircling our solar system at the edge of interstellar space, then any knocked loose fragments should take thousands of years to drift inward. Gravity is patient. Orbits are lazy ellipses stretching across centuries. Yet right now, as 3I Atlas, the third confirmed interstellar object ever detected, makes its way through our neighbourhood, we're seeing a spike in unusual high-inclination, low-albedo objects. Objects that seem to have no business being here yet. So we have to ask ourselves a question that sounds absurd until you sit with it for a moment. Is this a coincidence, or did Atlas drag something with it? Let me tell you what we know about 3I Atlas first, because it's already strange enough on its own. Discovered in 2025, this thing came screaming in from outside our solar system on a hyperbolic orbit, meaning it's not bound to the Sun. It's just passing through. Early observations using the Hubble Space Telescope estimate its nucleus somewhere between 440 meters and 5.6 kilometers across. That's a wide range, which tells you how hard it is to pin down the details of something moving that fast, that far away, wrapped in a glowing shroud of gas and dust. The object is designated as interstellar because its velocity and trajectory prove it didn't originate here. It came from somewhere else, another star system, another corner of the galaxy, and it punched straight through the Oort Cloud on its way in. Now, standard celestial dynamics are built on a simple foundation. Gravity is slow. When a rogue object passes through the Oort Cloud and gravitationally nudges a comet or chunk of ice, that comet doesn't immediately plunge toward the Sun. Instead, it begins a long, lazy spiral inward, taking millennia to complete. This is what happens when stellar flybys disturb the cloud. It's what happens when galactic tides tug on distant objects. The process is gradual, diffuse, spread across deep time. We call this the timing barrier. It's the reason we don't panic when something passes through the outer solar system. Because even if it shakes loose 1,000 comets, we won't see them. For generations. Our great-great-great-grandchildren might have to worry. We don't. Except that model assumes the disturbance is passive. It assumes the intruder just drifts by, gives a gentle gravitational nudge and moves on. But what if Atlas didn't drift? What if it dragged something? What if it triggered a cascade, a stream of debris that could arrive much sooner than the textbooks predict? This is the hypothesis that keeps a small number of astronomers awake at night, the ones willing to entertain extraordinary claims. They're suggesting that Atlas might not be travelling alone, that the bright glowing comet we can see, the one with the showy coma and tail, might just be the visible float in a much larger parade, and the rest of the parade is invisible, dark, already on its way. This isn't science fiction, this is pattern recognition meeting orbital mechanics meeting statistical anomaly. Because here's what nobody can quite explain. Why are we seeing more of these dark, high-inclination objects right now? Why does their arrival coincide so neatly with Atlas's passage? If this were purely random, you'd expect the flux to be constant year over year with small variations based on detection capabilities and survey coverage. But the numbers are ticking up. Not dramatically, not in a way that makes headlines, but enough to make people who stare at orbital catalogues for a living start asking uncomfortable questions. And then there's the wake. Reports, some from community telescope networks, some from independent observers with access to high-resolution infrared data, suggest something unusual about the space around Atlas. There's a region immediately surrounding the object, maybe a few astronomical units across, where dust and micrometeoroids seem surprisingly sparse. A clean zone, a void. And then, further back, maybe 2 or 3 astronomical units trailing behind, there are hints of enhanced particle density. A wake, as if Atlas swept through space like a broom, pushing debris aside, leaving a trail. This shouldn't happen with a normal comet. Comets shed material. They leave tails pointing away from the sun because solar radiation pressure blows gas and dust outward. You expect a smooth distribution, a diffuse coma, a predictable tail structure. You don't expect a cleaned-out zone with a dense wake trailing behind, unless something else is going on, unless Atlas is interacting with its environment in a way we don't fully understand yet. So here we are, watching an interstellar visitor slide through our solar system, and it's leaving fingerprints we can't quite read. And behind it may be a swarm of smaller, darker objects, invisible to most telescopes, already inbound, already committed to trajectories that will carry them past Earth's orbit in the coming years or decades. And we won't know they're there until they're close, very close. Could this be the start of an inbound swarm, or are we seeing patterns in noise connecting dots that don't form a picture? Future discoveries will tell us. But right now, the question hangs in the air like a held breath, and the clock is ticking. Part 2, the clean zone and trailing dust mystery. Comets are supposed to be messy. They're dirty snowballs, chunks of ice and rock that spend most of their lives frozen solid in the outer dark, only to wake up screaming when they get close to the sun. Heat triggers sublimation, ice turns to gas, and suddenly you've got a glowing coma wrapped around the nucleus and a tail stretching millions of kilometers behind. It's a predictable process, textbook stuff. Except 3i Atlas seems to have missed that chapter. Observers tracking Atlas noticed something odd early on. Around the nucleus, in the immediate vicinity of the object itself, there's less dust than expected. Not a dramatic absence, but a noticeable reduction. A clean zone. Normally, a comet sheds material continuously, creating a thick fog of particles that surrounds the nucleus like a shroud. But with Atlas, that shroud seems thinner, patchier, as if something swept the area clean, and then, further back, along the trajectory the object followed on its way in, there are hints of something else. Enhanced micrometeoroid density. Small particles, barely detectable, concentrated in a trailing region, maybe 2 or 3 astronomical units behind the comet. This is strange because it inverts the usual pattern. You expect the densest region of dust to be near the nucleus, where outgassing is most active, with a gradual thinning as you move away. But Atlas seems to show the opposite. A local void. A distant wake. It's like watching a boat move through water and seeing the waves pile up behind it instead of spreading evenly outward. So what could cause this? One possibility is outgassing dynamics. Comets don't shed material uniformly. Jets of gas can erupt from specific points on the surface, driven by uneven heating or subsurface pockets of volatile material. These jets can push dust in preferred directions, creating asymmetries in the coma and tail. Maybe Atlas has a particularly active jet pointing backward, or a series of jets that preferentially eject material along its trailing path. That would explain the wake. But it doesn't easily explain the clean zone, unless the outgassing is so directional that it actively clears the space around the nucleus, which would be unusual. Another interpretation borrows from fluid dynamics. When an object moves through a medium, it creates a slipstream. Water flows around a boat's hull, and in the wake behind, the flow becomes turbulent, churning, creating a region of disturbed water. Could Atlas be doing something similar as it moves through the sparse interplanetary medium? The solar wind, thin as it is, still contains charged particles, plasma, and micrometeoroids. If Atlas is moving fast enough, and if it's interacting with that medium in unexpected ways, maybe it's creating a pressure differential, pushing material aside, then letting it collapse back into a trailing wake. This would require Atlas to be denser or more massive than typical comets, or to have some surface property that enhances drag effects, but it's plausible, just barely. And then there's the more speculative idea. What if Atlas carries a magnetic or electromagnetic field? Not something we expect from a typical comet, but not entirely impossible either. If the nucleus has a high metallic content, or if it's surrounded by a plasma halo generated by intense outgassing of ionized gas, then charged particles in the surrounding space might respond to electromagnetic forces, not just gravity and radiation pressure. Charged dust, for instance, could be deflected or swept along field lines, creating complex patterns of accumulation and depletion. A magnetic bow shock, the kind you see around planets with strong magnetospheres, could plough through the interplanetary medium, pushing micrometeoroids into a trailing wake while leaving a relatively empty zone in the immediate vicinity. This is the kind of idea that makes mainstream astronomers uncomfortable because it requires invoking physics that isn't typically part of the comet playbook. Comets are supposed to be simple: ice, dust, a bit of rock. No fancy fields, no exotic interactions. But Atlas isn't a typical comet. It came from outside. It formed in a different stellar environment, under different conditions. Maybe it brought something unusual with it. Here's what makes this more than just academic speculation. Some observers, both professional and amateur, reportedly requested additional observation time specifically to map particle density in the region 5 to 10 astronomical units behind Atlas. They're checking the wake, quietly, without much publicity. Because if the wake is real, if there's genuinely a trailing stream of debris following this object, then we need to know what's in it, how dense it is, how fast it's moving, and whether any of it is on a collision course with Earth. Because that's the question that keeps surfacing, isn't it? If Atlas left a wake, and if that wake is full of small, dark fragments, what happens when Earth passes through it? Do we get a slow drizzle of micrometeoroids, barely noticeable, just an uptick in shooting stars and atmospheric entries, or do we get something worse? A rainstorm of debris, concentrated enough to pose a hazard to satellites, spacecraft, maybe even surface impacts if any fragments are large enough to survive re-entry. We don't know yet. The data is still being processed. The follow-up observations are ongoing. But the possibility is there, hanging in the background like a faint signal you can't quite tune in. And the longer we watch, the more the signal seems to solidify. Something is trailing Atlas. Whether it's dangerous or just interesting remains to be seen. But it's there, and it's coming our way. Part 3. The supposed X-ray halo and magnetic bow shock debate. Now we enter the realm of the truly strange, the kind of claim that gets whispered about in conference hallways but rarely makes it into peer-reviewed journals. Some early reports, unverified and contested, suggest that 3I Atlas might be surrounded by a wide X-ray halo. Not the faint X-ray emissions you sometimes see from comets, when solar wind ions collide with outgassing molecules. Something bigger. A plasma or magnetic envelope extending thousands, maybe hundreds of thousands, of kilometers from the nucleus. An active, energetic shell that shouldn't exist around a normal comet. Let me be clear, this remains speculative. No major observatory has published confirming data. The reports come from preliminary observations, from independent researchers analysing archival data, from people scanning X-ray and ultraviolet bands looking for anomalies. So take this with appropriate skepticism, but also understand why it matters. Because if Atlas really is wrapped in a strong magnetic or plasma field, then everything changes. Not just our understanding of this one object, but our assessment of the risks it poses to the inner solar system. Here's why. Magnetic fields interact with charged particles over enormous distances. Gravity is a long-range force, but it's weak. You need a lot of mass to exert meaningful gravitational influence. Electromagnetism, on the other hand, can act on individual ions, electrons, and charged dust grains with surprising strength, even when the source field is relatively modest. If Atlas carried a persistent magnetic field, and if that field extended far enough, then as it ploughed through the Oort Cloud, it wouldn't just gravitationally nudge objects, it would electromagnetically sweep them. Charged ice particles, ionized molecules, and dust grains with surface charges would respond to Lorentz forces, accelerating, deflecting, sometimes fragmenting, under the stress of rapid electromagnetic interactions. Think of it like this. A ship moving through water creates a bow wave because water has to move out of the way. The ship displaces the medium. But if the ship had a magnetic prow, and if the water contained iron filings, those filings wouldn't just get pushed aside, they'd get pulled along, swept into the wake, accelerated by the field. Atlas, if it carries such a field, could be doing the same thing to charged material in the Oort Cloud. Breaking apart weak aggregates, ionizing surfaces, and corralling debris into a trailing stream. This is speculative physics, I'll grant you, but it's not fantasy physics. Magnetic bow shocks exist. Earth has one. Jupiter has one. Any magnetized body moving through a plasma medium generates a shock front where the field lines compress and deflect incoming particles. The question is whether a comet, an icy body, could generate a field strong enough to matter. Typical comets don't. But Atlas isn't typical. It came from interstellar space. It might have a metallic core. It might have been exposed to conditions, magnetic environments, ionizing radiation that don't exist in our solar system. And if it retained some of that, if it brought a residual field or an active dynamo with it, then yes, it could produce a bow shock. The skeptics, and there are many, point out that standard comet models explain most of Atlas's behavior perfectly well. The coma, the tail, the non-gravitational accelerations, all consistent with gas sublimation and dust emission. You don't need to invoke exotic physics. Occam's razor suggests the simplest explanation is usually correct, and the simplest explanation here is that Atlas is just a comet. An unusual one, granted, with strange chemistry and an interstellar origin, but still fundamentally a comet. No magnetic tricks required. But absence of evidence isn't evidence of absence. Just because we haven't confirmed an X-ray halo doesn't mean it's not there. X-ray observations are difficult. They require space-based telescopes, limited observation windows, and careful data analysis to separate signal from noise. If the halo is faint, or if it's only intermittently active, or if it's structured in a way that makes it hard to detect from Earth's vantage point, we might miss it. Or we might only catch glimpses, fragmentary data that doesn't quite meet the threshold for publication but still nags at the back of your mind. What would settle this? Repeated targeted X-ray and radio observations, multiple instruments, different wavelengths, looking for persistent emissions or transient bursts. Magnetometer data if we could get a probe close enough, which we can't with current missions. Detection of charged dust or plasma trailing thousands of kilometers behind the nucleus, showing structure consistent with magnetic confinement or field line geometry. Any of these would be smoking gun evidence, but they're also difficult, expensive, and time-consuming to obtain, so we're left in a frustrating position. A tantalizing possibility, a mechanism that could explain some of the oddities, but not enough data to confirm or deny. And in the meantime, Atlas keeps moving. The wake, if it exists, keeps growing. And Earth's orbit, patient and predictable, continues to carry us toward whatever debris field might be waiting ahead. Part 4. The dark comet spike. Statistical anomaly or directed flux. There's a new term circulating in planetary science circles, one that didn't exist a few years ago. Dark comets. These are near-Earth objects that behave like comets, showing non-gravitational accelerations that suggest outgassing, but don't produce visible comae or tails. They're dark, low albedo, hard to spot, often detected only after close approach, sometimes only because they pass near enough to trigger tracking networks designed to catch potentially hazardous asteroids. They don't fit neatly into existing categories, which makes them interesting and also a little worrying. A 2024 study titled The Dynamical Origins of the Dark Comets and a Proposed Evolutionary Track analysed these objects and concluded that some likely originate from fragmentation cascades in asteroid belt resonances, not from traditional long-period comet reservoirs. They're fragments, pieces of larger bodies that broke apart, lost most of their volatile material, but retained just enough to produce faint outgassing. The study was careful, methodical, and didn't suggest anything alarming. Just a new class of objects to catalogue and understand. But here's what the study didn't address. Why are we seeing more of them now? The detection rate of dark comets, and of a typical high-inclination, low-albedo near-Earth objects in general, has been climbing. Not dramatically, but noticeably. And the timing of this uptick happens to coincide with Atlas's arrival in the inner solar system, which raises an uncomfortable question. Is this a detection bias, the result of better surveys and more sensitive instruments? Or is it a real increase in flux, a surge of new objects entering Earth-crossing orbits? Let me walk you through the statistics, simplified for those of us who don't live and breathe orbital catalogues. Every year, sky surveys detect a certain number of new near-Earth objects. That number has been rising steadily over the past 2 decades, which makes sense because we've built better telescopes, automated detection algorithms, and expanded survey coverage. If you plot detections over time, you expect a smooth upward curve reflecting improved capabilities. But if you filter the data, looking specifically at objects with high inclinations, low albedos, and orbital elements consistent with long-period origins, the curve gets bumpy. There's a spike, a statistical anomaly that's hard to explain purely by improved detection. Now, correlation isn't causation. Just because the spike coincides with Atlas doesn't mean Atlas caused it. Maybe it's a coincidence. Maybe there's another factor we're not considering. Maybe survey biases we haven't fully accounted for are skewing the numbers. But if you're the kind of person who takes risk assessment seriously, you can't just shrug and walk away. You have to ask the next question. If Atlas did disturb a previously stable population in the Oort Cloud, what would that look like? It would look like this. A sudden increase in the number of objects with orbital elements pointing back to the same general region of space Atlas came from. High inclinations, because Atlas arrived on a steeply inclined trajectory. Low albedos, because Oort Cloud objects are ancient, covered in radiation-darkened organic compounds, not the bright ice you see in fresh cometary nuclei. And scattered arrival times, because the disturbance wouldn't send everything inward at once. You'd get a stream, spread out over years or decades, with the fastest-moving fragments arriving, first and slower ones trailing behind. This is exactly the pattern some researchers are quietly investigating. They're correlating available orbital data, looking for clusters, checking whether the new detections share common ancestry. It's painstaking work. Orbits are messy. Perturbations from planets, the Yarkovsky effect, close encounters, all of these scramble the data and make it hard to trace objects back to their origins. But if a significant fraction of the recent dark comet detections can be linked to a common source region, that would be damning evidence. And then there's selection bias, the eternal nemesis of statistical analysis. Maybe we're just getting better at finding these objects. Maybe new infrared surveys, better algorithms, and expanded sky coverage explain everything. You can't rule that out, but you also can't assume it. Because even after correcting for detection biases, if there's still a statistically significant jump in 2025, then something real is happening. Something that doesn't fit the baseline model of steady-state flux from the Oort Cloud. Here's the risk scenario nobody wants to say out loud. Even if only a fraction of these dark comets are on Earth-crossing trajectories, and even if only a small percentage of those pose genuine impact risk, over decades that could translate to an elevated hazard. Not civilization ending, not extinction level, but enough to increase the probability of significant regional damage from an unexpected impact. And unlike bright comets that announce themselves months or years in advance, dark comets are stealthy. We might only get days or weeks of warning, maybe less. So we watch, we catalogue, we refine our models and argue over statistics and wait to see if the spike resolves into noise or solidifies into signal. And in the back of our minds, we wonder if Atlas was the herald of something larger, a cosmic Paul Revere announcing the arrival of an invisible army already on the march. Part 5. The Herder. Hypothesis. Atlas as a gravitational magnetic tractor. Let me introduce you to an idea that sounds like science fiction but rests on plausible physics. What if 3i Atlas isn't just a passive visitor drifting through our solar system? What if it's a tractor, a herder, gravitationally tugging or magnetically shepherding a swarm of smaller bodies? And what if that changes everything about the timeline we expect for Oort Cloud disturbances? Here's the standard model. An object passes through the Oort Cloud. Its gravity perturbs nearby objects, nudging them onto new orbits. Some of those objects eventually spiral inward toward the Sun, but the process takes millennia because the initial perturbations are small and the distances are enormous. This model works beautifully for stellar flybys, for galactic tides, for any distant, slow-moving perturber. But it breaks down if the perturber is fast, compact, and interacting with material in unexpected ways. Atlas is fast. It came in at roughly 44 kilometers per second and accelerated to around 150,000 miles per hour at perihelion. That's blistering speed on a solar system scale. And if it passed through a denser than average region of the Oort Cloud, a pocket where objects cluster more tightly than the average distribution, then its gravitational influence wouldn't just nudge things, it would yank them, drag them, potentially capturing a heterogeneous swarm of smaller bodies in its gravitational wake, like a cosmic freight train pulling a string of cars. Now this requires Atlas to be more massive than typical comets, or denser, or both. Standard comet models based on observed coma brightness and tail structure suggest masses in the range of a few billion to a few tens of billions of kilograms. That's not nothing, but it's not enough to gravitationally bind a swarm of objects over interstellar distances. Unless the objects are very small, or unless they're already loosely clustered, and Atlas just happened to plough through at the right moment, sweeping them up like a snowplow on a highway. But add in electromagnetic effects, and the picture changes. If Atlas carries a magnetic field, as suggested by the speculative X-ray halo reports, then it doesn't need to rely solely on gravity. Charged particles, ionized molecules, and dust grains with surface charges would respond to the field. Over time, over the long journey from the outer Oort cloud to the inner solar system, electromagnetic forces could corral material, concentrating it into a stream that follows Atlas's trajectory. It's a kind of cosmic shepherding, using field lines instead of gravity wells to keep the flock together. What would such a payload look like? A heterogeneous mix of small, dark, low-albedo comets or comet fragments. Objects too small to produce visible comae, or objects whose volatile content has been depleted by radiation or sublimation over eons of interstellar travel. They'd be largely invisible to optical surveys, detectable only by their gravitational signatures or by infrared emissions if they happen to get close enough to the sun to warm up, and they'd be spread out, not clustered in a tight group, but strung along Atlas's orbital path like beads on a thread. If this hypothesis is correct, then the normal multi-millennium lag time between Oort cloud perturbation and inner solar system arrival collapses. Years, decades, not centuries, because the swarm isn't travelling independently, each fragment on its own slow orbit. They're being dragged, pulled along in Atlas's wake, moving at the speed of the tractor, not at the leisurely pace of gravity-perturbed debris. This is where mainstream astronomers get off the bus, because observational data so far, everything we've measured, supports a normal comet model. The coma shows gas emission lines consistent with sublimation of volatiles. The tail structure follows expected, patterns for dust and ion tails driven by solar radiation and the solar wind. Non-gravitational accelerations match what you'd predict from asymmetric outgassing, and recent composition measurements, showing unusually high carbon dioxide to water ratios, suggest strange chemistry but not necessarily exotic structure. So Occam's razor tells us to stick with the simple explanation. Atlas is a comet. An interesting one. A chemically unusual one. But still a comet. No need to invoke electromagnetic herding or gravitational tractors or trailing swarms of dark debris. Except that Occam's razor also tells us to pay attention to anomalies. The clean zone, the trailing wake, the dark comet spike, the timing. Individually, each one can be explained away. Collectively, they form a pattern. And patterns are how we find new physics. What if Atlas is only the visible float in an invisible parade? What if the shiny, glowing comet nucleus, the thing we can see and photograph and study, is just the tip of the iceberg? And the real mass, the real danger, is the swarm trailing behind, still months or years away from detection. If that's the case, then we're looking at the wrong thing. We're watching the distraction, the decoy, while the real bombardment approaches unseen. This is speculative, unproven, based on fragmentary data and contested observations, but it's also the kind of speculation that planetary defense takes seriously, because if there's even a small chance it's correct, the implications are too significant to ignore, so we keep watching, keep tracking, keep asking uncomfortable questions, and we wait to see if the invisible parade reveals itself, or if it's already here, just too dark to see. Part 6. The Hidden Files, 2005 to 20. 20. NEO Focus Reinterpreted. Planetary defense became a serious priority in the early 2000s, not because of a specific threat, but because we finally had the technology to do something about it. Sky surveys expanded, tracking networks were built, radar systems were upgraded. The goal was simple: find every near-Earth object larger than 140 meters, catalogue its orbit, and make sure none of them are on a collision course with Earth. This effort intensified over the next 2 decades, culminating in sophisticated automated systems that scan the sky nightly, flagging new detections and refining orbits for known objects. But what if that increased attention wasn't just routine? What if some of it was driven by early detection of subtle changes in background flux, patterns that didn't fit the expected steady-state distribution of near-Earth objects? What if someone noticed something years ago and quietly started looking harder without broadcasting their concerns? This is where we enter the realm of archival data reinterpretation. Go back through the records, look at detection rates for long-period objects, high inclination inbounds, low albedo, fragments, plot them over time, filter for objects that appear suddenly, with poorly constrained orbits that were tracked for a few days and then lost. See if there's a pattern, a clustering, an uptick that started not in 2025 but earlier, maybe in the 2010s or even the 2000s, subtle enough to be dismissed as noise at the time but suspicious in hindsight. Some amateur astronomers and small observatories have been doing exactly this. Digging through old logs, cross-referencing detection reports, compiling lists of weird inbound objects that were later classified as unknown or lost to follow-up. These aren't peer-reviewed studies. They're anecdotal. They're the kind of data that gets shared on forums and in private emails, not in journals. But anecdotal doesn't mean wrong. It means unverified. And sometimes unverified data points to something real. Here's an example. In 2008, a small observatory in Australia reported an unusual object on a high-inclination trajectory, moving fast with an orbit that suggested either a very eccentric comet or a fragment of something larger. They tracked it for 3 nights, submitted their observations to the Minor Planet Center, and then nothing. The object was never recovered. Too faint, too fast, not enough data to refine the orbit for follow-up. It went into the catalogue as a lost object, a statistical blip. But what if it wasn't a blip? What if it was the first hint of a stream, a fragment from a disturbance that happened decades earlier, finally arriving in the inner solar system? Multiply that by dozens of similar cases over the past 20 years, and you start to see a different picture. Not a sudden spike in 2025, but a slow, gradual increase stretching back further than we thought. A long wavelength signal buried in the noise, only visible now because Atlas made us look harder. This matters because if the process began decades ago, then Atlas isn't the source. It's a marker, a wake-up call. The disturbance happened before Atlas arrived, maybe from a previous stellar flyby, or from a compact object passing through the Oort Cloud that we never detected because it didn't produce a visible signature. And Atlas, arriving now, is just the most obvious herald of something that's been building for years. The counter-argument is obvious. Improved detection capabilities explain everything. Better telescopes, better algorithms, more survey coverage. We're finding more objects because we're looking harder, not because there are more objects to find. This is true. Detection biases are real and significant, but they don't explain everything. You can correct for biases. You can model expected detection rates based on instrumentation improvements. And if, after corrections, you still see an excess, then something real is happening. The other counter-argument is psychological. Humans are pattern recognition machines. We see faces in clouds, conspiracies and coincidences. Maybe there's no hidden signal. Maybe we're just connecting dots that don't form a picture because we want there to be a picture. Because a random, chaotic universe is scarier than a universe with patterns, even dangerous patterns. But here's the thing. Planetary defense is built on taking unlikely scenarios seriously. The dinosaurs didn't worry about asteroids either. They probably thought the sky was safe, right up until it wasn't. So we check. We archive data. We reanalyze old observations. We take the anecdotal seriously enough to verify or debunk it. Because the cost of being wrong, of dismissing a real signal as noise, is too high. So we ask ourselves, what would a decades-long disturbance look like in the data? And are we seeing it? The answer is still unclear, but the question is no longer absurd, and that alone should make us pay attention. Part 7. A precedent. What happens when a stellar flyby disturbs the Oort Cloud? 70,000 years ago, a red dwarf star named Schultz's star passed within about 1 light-year of our solar system. That's close, cosmically speaking. close enough that its gravity might have given a gentle tug to the outermost fringes of the Oort Cloud, perturbing a few thousand icy bodies, nudging them onto new orbits that would eventually carry them inward toward the Sun. Computational models suggest that some of those bodies are still on their way. They won't arrive for thousands of years, maybe tens of thousands, but they're coming. This is how stellar flybys work. Slow, patient, diffuse. The encounter happens over centuries as the star approaches, passes, and recedes. The gravitational influence is weak, spread out over enormous distances. Objects get nudged, not yanked. Orbits shift by tiny amounts, angles change by fractions of a degree, and the result is a long, drawn-out increase in the flux of long-period comets entering the inner solar system. A rain, not a storm, spread across millennia. Now contrast that with 3I Atlas. Atlas came in fast, 44 kilometers per second, and it didn't circle politely like a visiting dignitary. It punched straight through. At perihelion, it was moving at 150,000 miles per hour, slingshotting around the Sun, and already accelerating back out toward interstellar space. The encounter time was brief, weeks, maybe months, depending on how you define the boundary of gravitational influence. But brief doesn't mean gentle, because speed matters, momentum matters, and a compact, fast-moving object can deliver a sharp, localized kick to anything in its path. Here's where the models get interesting. Most orbital simulations assume perturbers are either distant and slow, like stellar flybys, or local and bound, like planets and giant comets on stable orbits. They don't typically model fast, compact, unbound intruders passing directly through dense regions of the Oort Cloud. Why? Because until recently we didn't have confirmed examples of interstellar objects. Oumuamua was the first, in 2017. Borisov was the second, in 2019. Atlas is the third. We're still learning what's normal for this class of visitor, but some rare computational studies, usually unpublished or buried in technical reports, have explored what happens when a compact intruder passes through a localized density enhancement in the Oort Cloud. And the results are surprising. Under specific conditions, if the intruder is massive enough, fast enough, and if the local density is high enough, you don't get a diffuse rain. You get a coherent stream, a directed flux. Objects get yanked onto similar trajectories, clustering in orbital element space, arriving in waves rather than trickling in over millennia. This is rare. It requires the parameters to align just right. The Oort Cloud is not uniformly distributed. Theoretical models suggest it has structure, filaments, pockets of enhanced density left over from the solar system's formation or sculpted by previous perturbations. If Atlas happened to pass through one of those pockets, if it threaded the needle through a dense clump of objects, then the risk of a directed stream increases dramatically. And here's the kicker. We don't know the Oort Cloud structure, not in detail. We can't directly observe it. It's too far, too diffuse, too dark. We infer its existence from the long-period comets that fall inward and from theoretical models of solar system formation. But those models make simplifying assumptions. They assume smoothness, isotropy, statistical homogeneity. Real structure, real clumps and voids and filaments get averaged out. So when Atlas came through, we don't know what it hit. Maybe it passed through empty space, perturbing nothing, leaving no wake. Or maybe it ploughed through a dense filament, a cosmic highway littered with icy debris, and kicked thousands of objects loose. We won't know until they arrive. If they arrive. The implication for risk assessment is straightforward. If Atlas encountered a dense pocket, then the textbook model of long-period comet flux no longer applies. The arrival time collapses. Instead of centuries, we're talking decades. Instead of a few extra comets per year, we're talking dozens, maybe hundreds. And because these objects are dark, old, radiation darkened, and lacking active comae until they get close to the Sun, we might not see them until it's too late to do anything about them. This is why some astronomers are quietly nervous, not panicking, not predicting doomsday, but acknowledging that the standard models might not cover this scenario. And when models fail, when reality diverges from expectation, that's when surprises happen, and surprises, in the context of planetary defense, are never good. Part 8. The Chaff. Concept: weaponized debris in planetary defense strategic theory. Let me borrow a metaphor from military technology. During the Cold War, missile designers developed a concept called MIRV, Multiple Independently Targetable Reentry Vehicles. One missile carries several warheads, each capable of hitting a different target. The idea was strategic. One launch vehicle saturates defenses with multiple threats, making interception difficult. If you're defending a city and you see one incoming missile, you focus all your countermeasures on that single target. But if that one missile splits into 10 warheads, each following a different trajectory, suddenly your defensive calculations become exponentially more complex. Which warhead is real? Which are decoys? Do you have enough interceptors to stop them all? The mathematics of defense collapse under saturation. Around the same time, electronic warfare introduced chaff, strips of metal or metallized material released by aircraft to confuse radar systems. The radar sees hundreds of returns, most of them false, and can't distinguish the real target from the decoys. Pilots would dump chaff clouds and slip away in the confusion, invisible among 1,000 false signatures. The technology was elegant, simple, and devastatingly effective. You don't need to destroy the radar, you just need to blind it with noise. Now apply that concept to cosmic scales. Imagine 3i Atlas as the battering ram, the visible part of the attack. It comes in bright, glowing, with a showy coma and tail drawing all the attention. Every telescope, every tracking system, every astronomer with access to observing time points at this magnificent interstellar visitor. We photograph it, we analyze its spectrum, we calculate its orbit, we write papers, we hold press conferences. Meanwhile, trailing behind, invisible in the glare, a field of small dark bodies. Thousands of them, maybe tens of thousands. Each too small to pose a civilization-ending threat individually, but collectively overwhelming detection systems, saturating tracking networks, making it impossible to catalogue and assess every object. This is the chaff concept, and it's not as absurd as it sounds, because if Atlas were artificial, or if it were modified, engineered, repurposed by some intelligence for strategic purposes, then deploying a debris field makes sense. It confuses, it distracts, it creates noise in the data, making it harder to identify high-priority targets. And in the context of planetary defense, where resources are limited and tracking networks can only follow so many objects at once, saturation is a genuine vulnerability. Our systems are designed to track thousands of objects, yes, but not millions. Not simultaneously, not with the resolution needed to assess size, composition and trajectory for each one. Let me be clear, there is no credible evidence that Atlas is artificial. None. Spectroscopic observations show composition consistent with natural ices and organics, carbon dioxide and water, and trace amounts of other volatiles you'd expect from a comet. The coma and tail behavior match what you'd expect from sublimation-driven outgassing. Gas expanding from the nucleus as sunlight heats the surface. Orbital dynamics are consistent with a natural interstellar trajectory, a hyperbolic path that requires no propulsion, no course corrections, just the natural motion of an object falling through the sun's gravity well and back out again. Every mainstream analysis treats Atlas as a comet. A weird comet, yes, with unusual chemistry and an interstellar origin, but a comet nonetheless. But here's the thing. The chaff concept doesn't require Atlas to be a spaceship. It doesn't require intent or engineering or some alien civilization playing four-dimensional chess with our planetary defense systems. It could be unintentional, a natural process that produces the same result. If Atlas, during its journey through interstellar space or during passage through the Oort Cloud, fragmented, shedding debris, creating a wake of smaller bodies, then the effect is the same: saturation. Too many targets to track effectively, and if those fragments are dark, low albedo, lacking visible comae because they're too small or too depleted of volatiles, they become invisible until they're dangerously close. Fragmentation happens. We've observed it in solar system comets. Comet Shoemaker-Levy 9 broke into more than 20 fragments before slamming into Jupiter in 1994. Comet Schwarzmann-Wachmann 3 split into multiple pieces during its 26 perihelion passage. Thermal stress, rotational forces, tidal effects, all of these can tear a comet apart. An Atlas, having travelled through interstellar space for potentially millions of years, exposed to cosmic rays, temperature fluctuations, and occasional impacts from interstellar dust, might have developed structural weaknesses, cracks, fissures, zones of mechanical failure waiting for the right trigger to break apart. Compare this to known patterns in terrestrial contexts. Satellite megaconstellations like those being deployed in low Earth orbit create a similar problem. Thousands of small reflective objects cluttering near Earth space, making it harder to track operational satellites, debris, and potential collisions. Astronomers complain that these constellations ruin observations, creating streaks across images, interfering with sensitive surveys. Space traffic management agencies struggle to model collision probabilities when the number of tracked objects exceeds their computational capacity. It's a saturation problem, not because any individual satellite is dangerous, but because the aggregate creates an environment where tracking becomes unreliable. Or consider industrial debris fields, clouds of junk left over from manufacturing or mining operations, spreading out over time, becoming harder to monitor as the pieces disperse. Anti-satellite weapon tests have created similar problems, shattering satellites into thousands of fragments that will orbit Earth for decades, each one a potential collision hazard, each one requiring catalogue entry and tracking resources. The international space community has started calling these events debris-generating incidents, and warning that too many of them could render certain orbital zones unusable. Kessler syndrome, the cascading collision scenario where debris begets more debris until orbital space becomes impassable. Atlas, intentionally or not, could be creating a cosmic debris field, and that field, if dense enough, complicates planetary defense, because you can't intercept what you can't see, you can't assess risk for objects you haven't detected, and if the real threat, the genuinely dangerous fragments, are hidden among thousands of harmless dust specks, how do you prioritize? How do you decide what to track closely and what to ignore? Do you spend resources calculating orbits for every faint blip in the telescope data, knowing that 99% will turn out to be harmless? Or do you filter, apply detection thresholds, and risk missing the one object that actually poses a threat? This is speculative strategic theory, the kind of scenario that gets wargamed in classified briefings and academic workshops. Defense analysts and planetary scientists sit in windowless rooms and ask uncomfortable questions. What if an adversary wanted to attack Earth, but knew we had tracking systems? How would they bypass detection? Could they use natural objects as cover? Could they deliberately create debris fields to overwhelm our sensors? These aren't predictions, they're possibilities. Thought experiments designed to stress test our defensive capabilities and identify vulnerabilities before someone exploits them. And the vulnerabilities are real. Our detection systems are good but not perfect. Survey telescopes scan the sky systematically, but they have limiting magnitudes, thresholds below which objects become invisible. Our tracking networks are comprehensive but finite, capable of following thousands of objects but not millions. Computational resources for orbit determination and conjunction analysis are substantial, but not unlimited. And saturation, overwhelming the system with too many targets, is a known failure mode. It's the same principle that makes MIRV missiles effective, that makes chaff useful, that makes denial of service attacks work in cybersecurity. Flood the system. Exceed its capacity. Watch it fail. So we ask the uncomfortable question, what if Atlas isn't the threat? What if it's the distraction? What if the real danger is the invisible swarm trailing behind, and by the time we notice, it's already too late to respond effectively? This is nightmare fuel for planetary defense planners. The scenario where you're watching the wrong thing, tracking the obvious target while the real danger slips past unnoticed. It's the magician's misdirection on a cosmic scale. Look at my right hand while my left hand palms the card, and it's why even speculative scenarios, even ideas that sound like science fiction, get taken seriously. Because underestimating an unlikely threat is how catastrophes happen. Because the cost of being wrong, of dismissing a real danger as impossible or absurd, is measured in lives, infrastructure, and potentially civilization itself. Planetary defense operates under a precautionary principle. Take threats seriously even when probability is low. Investigate anomalies even when natural explanations exist. Build redundancy into detection and tracking systems so that saturation is harder to achieve. Atlas might be entirely natural. A comet, nothing more, passing through on its way back to interstellar space. But it might also be a lesson, a demonstration of vulnerability, a proof of concept showing that our planetary defense systems can be confused, distracted, and overwhelmed by swarms of small objects. Whether the lesson comes from nature or from something else, we'd be wise to learn it, to shore up our detection capabilities, to develop better filtering algorithms that can separate signal from noise without missing critical targets, to build tracking networks with excess capacity so that saturation becomes mathematically impossible. Because the next interstellar visitor might not be so polite, might not announce itself with a bright coma, might not follow a predictable trajectory. And if it brings friends, if it comes with a debris field or fragments or companions hidden in its wake, we need to be ready. Not panicked, not paranoid, but prepared, aware of the vulnerabilities, conscious of the gaps in our defenses, and willing to take seriously even the scenarios that sound, on the surface, like they belong in a thriller novel rather than an academic journal. Part 9. Chemistry and Spectroscopy. Oddities. The non-coma coma. Comets are supposed to smell like water. Well, not literally smell, but spectroscopically speaking, water dominates their emission profiles. When sunlight heats a comet's surface, water ice sublimates, turning directly from solid to gas, creating the characteristic coma and tail we associate with these objects. Carbon dioxide is also present, sometimes in significant amounts, but usually as a minor component compared to water. This is the standard profile. This is what textbooks say. This is what generations of astronomers have observed, measured, and catalogued. Water is the baseline, the foundation, the thing that makes a comet a comet. 3i Atlas didn't get the memo. Early observations using ground-based and space-based spectrographs revealed something unusual. The ratio of carbon dioxide to water in Atlas's coma is extreme, at least 8:1, possibly higher. That's among the most carbon dioxide-rich compositions ever measured in a comet. And it's not a measurement error. Multiple independent observations confirm it. Different instruments, different teams, different observing conditions, all arriving at the same conclusion. Atlas is drowning in carbon dioxide while water, the substance we expect to see dominating the show, barely registers. Why does this matter? Because composition tells you about formation conditions. Water-rich comets likely formed in regions where water ice was abundant, either in our own solar system's outer reaches or in similar environments around other stars. These are the cold zones beyond the frost line, where temperatures drop low enough for water to freeze solid and accumulate into planetesimals, the building blocks of comets and planets. Carbon dioxide-dominated comets suggest different conditions, colder, more distant. Regions where carbon dioxide could condense but water remained gaseous or was simply less available. Or perhaps Atlas formed closer to its parent star, where intense radiation processed surface materials, depleting water through photodissociation and concentrating more volatile carbon compounds that could survive in that harsh environment. This is strange but not necessarily exotic. Comets can have weird chemistry. Borisov, the second interstellar object discovered in 2019, also showed unusual composition, with higher than expected carbon monoxide and other volatiles that didn't match solar system norms. These objects formed elsewhere, under different stellar conditions, orbiting stars with different masses, different luminosities, different chemical environments. So we expect some diversity. We expect surprises. The universe is not a monoculture, and comets that formed around red dwarfs or massive blue stars should look different from comets that formed around sun-like stars. That's basic astrophysics. But the carbon dioxide dominance in Atlas raises another possibility, one that's more speculative and harder to test. What if the coma is hiding something? What if the outgassing we observe, the glowing shell of gas and dust surrounding the nucleus, is a kind of camouflage, intentional or not, that obscures the true nature of the object beneath? A hollow shell, perhaps, or a dense nucleus coated in volatile ices that produce unusual emission patterns. Or maybe the nucleus has developed a thick insulating crust that suppresses water sublimation, allowing carbon dioxide, which sublimates at lower temperatures, to dominate the visible outgassing. Let me unpack that last point because it's actually more plausible than it sounds. Comets can develop surface crusts through repeated passages near the Sun, or through long exposure to cosmic rays in interstellar space. These crusts form when the outer layers lose their volatiles, leaving behind a residue of dust, organics, and refractory materials that acts as insulation. Beneath this crust, pristine ices remain locked away, unable to escape until the crust fractures or erodes. If Atlas developed such a crust during its long journey through interstellar space, then water ice might be present in abundance internally, but unable to sublime it effectively. Meanwhile, carbon dioxide, which has a lower sublimation temperature, could escape through cracks and pores in the crust, dominating the visible emissions even though it's not the dominant component by mass. This scenario explains the observations without invoking anything exotic. It's a natural process, well documented in solar system comets that have become mantled or inactive after multiple perihelion passages. But it also raises uncomfortable questions. If the crust is hiding the true composition, then how do we know what Atlas is really made of? How do we estimate its mass, its density, its internal structure, if the only thing we can measure is the thin shell of gas escaping from the surface? This is the kind of speculation that makes mainstream scientists roll their eyes. Because if you can't test it, if you can't devise an observation that would confirm or rule out the hypothesis, then it's not science, it's storytelling. And maybe that's fair. Science demands testability. It demands falsifiability. You can't just spin narratives and call them theories. But storytelling has value when it expands the possibility space, when it makes you look at data differently and ask questions you wouldn't have asked otherwise, when it forces you to confront the limits of what you can observe and measure. So let's ask the question. If Atlas has a dense, possibly metallic core hidden beneath a shell of volatile ices, how would we know? The coma would still look normal, more or less. The tail would still form driven by solar radiation pressure and the solar wind acting on dust and ionized gas. The spectroscopic signature would be dominated by the surface materials, the stuff that's actively sublimating and glowing in ultraviolet and visible light. But the mass distribution, the density, the internal structure, could be very different from what we assume based on typical comet models. And if the structure is different, then the mass could be different, significantly different. Standard comet models estimate mass based on coma brightness, tail structure, and non-gravitational accelerations caused by outgassing. These methods work reasonably well for normal comets, where you can assume a fluffy, porous structure with density similar to freshly fallen snow, or maybe compact ice. But if Atlas has a dense core, the estimates could be off by factors of 10 or more. A small bright object with a dense core could have far more mass than a large, faint object with a fluffy interior, and mass matters because mass determines gravitational influence. Which feeds back into the Herder hypothesis, the idea that Atlas might be dragging a swarm of smaller objects in its wake. A denser nucleus means more mass, more gravitational pull, more capacity to perturb and capture debris as it ploughed through the Oort Cloud. Instead of being a modest-sized comet with typical influence, Atlas could be a heavyweight, punching above its apparent size class, exerting gravitational forces strong enough to meaningfully alter the trajectories of thousands of nearby objects. And if that's true, then the risk assessment changes, because more mass means more perturbation, which means more debris kicked loose, which means more potential impactors heading toward the inner solar system. But we don't have direct measurements of Atlas's internal structure. We can't land a probe on it, not with current technology and not on such short notice. We can't drill into it or perform seismic analysis or use ground-penetrating radar to map subsurface layers. All we have are remote observations limited to what we can see from Earth or from space-based telescopes millions of kilometers away. And those observations show unusual chemistry but nothing definitively exotic. No emission lines from metals that shouldn't be there. No compounds that scream artificial or engineered. No smoking gun, just carbon dioxide, lots of it. And a nagging sense that we're missing something. There's another angle to consider here, one that ventures even further into speculative territory, but deserves mention in a what-if exploration. What if the unusual chemistry isn't hiding something solid but something dynamic? What if Atlas is actively processing material, breaking down complex molecules through some mechanism we don't understand, producing carbon dioxide as a byproduct? This sounds like chemistry, not physics, but in the cold, radiation-soaked environment of interstellar space, strange chemical reactions can occur. Cosmic rays can break molecular bonds, ultraviolet radiation can drive photochemical reactions, and over millions of years of exposure, surface materials can be transformed into compounds that don't exist naturally in our solar system. Some researchers have proposed that interstellar objects might carry organic compounds synthesized in environments very different from anything we know. Complex carbon chemistry, driven by radiation rather than heat, producing molecules that we wouldn't recognize or wouldn't expect to see. If Atlas harbors such chemistry, then the carbon dioxide we observe might be the result of ongoing decomposition, volatile compounds breaking down as the comet warms approaching the Sun. The outgassing wouldn't be simple sublimation, but a complex cascade of chemical reactions, each step producing different gases, with carbon dioxide emerging as the dominant endgame product. This is extremely speculative. We have no direct evidence for exotic chemistry beyond what normal comet models can explain, but the possibility exists, tucked in the margins of what's theoretically plausible, waiting for better observations or future missions to confirm or dismiss. And in the meantime, it serves as a reminder that interstellar objects are genuinely alien, formed under conditions we can barely imagine, carrying chemical and physical properties that challenge our earthbound intuitions. So we're left with questions. Is Atlas just a carbon dioxide-rich comet, formed in an unusual environment around a distant star, now passing through our solar system on its way back to interstellar space? An interesting anomaly, worthy of study but fundamentally understandable within existing frameworks? Or is there something else going on? Something hidden beneath the glowing shell? Something we can't see because we're not looking in the right way, or because our instruments aren't sensitive enough to detect the subtle signatures? The data doesn't answer that yet, but it keeps the question open. And in science, keeping questions open is how discoveries happen. You don't advance knowledge by assuming you understand everything. You advance by noticing the things that don't quite fit, the anomalies that nag at the edge of your understanding, the patterns that seem almost but not quite explicable. Atlas's chemistry is one of those patterns, unusual enough to warrant attention, strange enough to spark speculation, but not yet definitive enough to demand revision of fundamental theory. And maybe that's where we should be. Curious but cautious, intrigued but skeptical. Watching Atlas as it moves through the solar system, gathering every scrap of data we can, looking for additional clues that might resolve the ambiguity. Because the truth, whatever it is, lies in the data. And the data, for now, is still incomplete, still evolving, still capable of surprising us with each new observation. Part 10. Oort Cloud Topology and the Blind Spots. No one talks about. The Oort Cloud is not a neat symmetrical shell. It's not a smooth bubble of icy debris wrapped evenly around the Sun, at distances between 2,000 and 100,000 astronomical units. That's the simplified version you see in diagrams, the one that makes the solar system look tidy and comprehensible. Reality is messier. The Oort Cloud is asymmetric, clumpy, riddled with density fluctuations and structural asymmetries sculpted by billions of years of galactic tides, stellar flybys and planetary perturbations. Think of it as a cosmic junkyard, not evenly distributed but patched and chaotic. Some regions are nearly empty, voids where objects have been cleared out by previous disturbances. Other regions are denser, pockets where material has accumulated, possibly in filaments or streams left over from the solar system's formation, or captured from passing molecular clouds. Theoretical models suggest these structures exist, but observational confirmation is nearly impossible. The Oort Cloud is too far, too faint, too diffuse to image directly. We infer its properties from statistical analysis of long-period comets and from simulations. This matters because if 3I Atlas passed through a dense pocket, a region where objects cluster more tightly than average, then the number of disturbed bodies could be significantly higher than baseline estimates. Standard models assume a uniform distribution. Plug in Atlas's trajectory, calculate the volume of Oort Cloud it passed through, estimate the average number density, and you get a prediction for how many objects might have been perturbed. But if the density isn't uniform, if Atlas happened to thread through a filament, those predictions are wrong. Potentially very wrong. Let me paint you a picture of what we're actually dealing with here. Imagine the Oort Cloud as an ancient battlefield, scarred by 4.5 billion years of cosmic warfare. Every time a star passed within a few light years of our solar system, it left gravitational scars. Every time the Sun bobbed up and down through the galactic plane, tidal forces reshaped the distribution. Every time a molecular cloud wandered by, it captured some objects and released others. The result is not smooth, it's textured, wrinkled, full of structure at every scale we can measure and probably at scales we can't. Some advanced dynamical studies, mostly unpublished or buried in technical conference presentations, have explored the possibility of Oort Cloud filaments. These are elongated structures, streams of objects aligned along preferred directions, possibly shaped by resonances with the galactic potential or by tidal forces from nearby stars. If such filaments exist, and if Atlas's inbound trajectory intersected one, then instead of perturbing a random scattering of objects, it would plough through a concentrated stream, kicking loose hundreds or thousands of bodies all moving in roughly the same direction. This is speculative topology, extrapolating from limited data and theoretical models. But it's not baseless. We see similar structures in other contexts. Planetary rings show gaps and resonances carved by the gravitational influence of moons and the complex interplay of orbital dynamics. Asteroid belts have Kirkwood gaps where Jupiter's gravity clears out certain orbits like a cosmic vacuum cleaner. Molecular clouds in interstellar space form filaments and sheets, not uniform spheres, shaped by turbulence, magnetic fields, and self-gravity. Why would the Oort Cloud be any different? Why would we assume that the most distant, most ancient structure in our solar system follows simple rules when nothing else does? The answer is we wouldn't, except that it's convenient. Uniform distributions are easy to model. They produce clean predictions. You can write the equations on a single page and calculate expected flux rates without breaking a sweat. But convenience doesn't equal accuracy, and when you're assessing existential risks, when you're trying to predict whether Earth might face an elevated bombardment rate, convenience is a luxury you can't afford. Now tie this back to Atlas's reconstructed trajectory. By analysing its velocity and direction as it entered the inner solar system, astronomers can trace its path backward, extrapolating where it came from. The trajectory suggests Atlas passed through a region of the Oort Cloud at high galactic latitude, moving at a steep angle relative to the ecliptic plane. That's consistent with an interstellar origin, coming in from outside the solar system, punching through at an angle that most objects in our solar system never experience. But it also means Atlas crossed through regions that might be more structured, less depleted than the average Oort Cloud volume. High galactic latitudes are interesting because they're less affected by the galactic plane's tidal forces, which tend to strip away material from the cloud's outer edges. Objects at high latitudes might have survived longer, accumulated in greater numbers, formed denser concentrations. If Atlas came in from above or below the galactic plane, it might have encountered one of these preservation zones, regions where the Oort Cloud retains more of its original structure and density. And if that's the case, then the perturbation could be more severe than models predict. If there's a dense filament there, and if Atlas disturbed it, then we should see evidence in the form of increased flux of long-period comets, with similar inclinations and orbital elements. This is testable. You can look at recent detections, filter for high-inclination objects, check if they cluster in a way that suggests a common source region. The data is noisy, and the statistics are complicated by detection biases, but it's doable. Some researchers are doing exactly this, quietly, without much publicity, because if they find a significant cluster, it confirms the filament hypothesis, and if the filament hypothesis is correct, then the risk assessment changes dramatically. Because a filament means a pulse, not a steady drizzle. It means objects arriving in waves, concentrated over decades instead of spread over millennia. And it means Earth, patient and predictable in its orbit, might pass through regions of enhanced debris density in the coming years. Regions where the probability of a close encounter, or worse, an impact, rises above baseline. This is not about single catastrophic collisions. This is about statistical risk elevation. More objects means more chances for something to go wrong, more chances for a fragment to have Earth's name on it. The mathematics of filamentary structures is complex, but the intuition is simple. Imagine a stream of traffic on a highway. If cars are evenly spaced, you can cross the highway safely by timing your run between vehicles. But if the cars are bunched into convoys, with long gaps between them, then your crossing strategy changes. You wait for a gap, then sprint. Or you get caught in the convoy and become roadkill. The Oort Cloud, if it has filamentary structure, creates similar bunching. Long periods of relative quiet, then pulses of activity when Earth's orbit intersects a debris stream. We've seen this pattern before, on smaller scales. Meteor showers happen when Earth crosses the orbital path of a comet, encountering the dust and debris the comet left behind, the Perseids, the Leonids, the Geminids, all caused by Earth passing through cometary debris streams. These are predictable, annual events because we know where the streams are, and we can calculate when we'll hit them. But what if there are larger, older, more diffuse streams we haven't mapped yet? Streams left by long-period comets that passed through millennia ago, or streams kicked up by interstellar visitors we never detected. Atlas could be creating one of those streams right now, or it could have passed through an existing stream and disturbed it, sending material cascading inward on new trajectories. Either way, the result is the same: enhanced risk, elevated flux, a temporary but significant increase in the probability of impacts or close encounters. The challenge is detection. How do you confirm a structure you can't see directly? You rely on statistical inference, on patterns in the data, on correlations between observed objects and theoretical predictions. It's slow work, it's uncertain, but it's the best we can do. And until we have better data, until we build telescopes that can image the Oort Cloud directly, or send probes to sample it, we're left with models and guesswork, and the uncomfortable awareness that there are blind spots in our understanding, places where monsters might hide. Those blind spots are literal. There are regions of the sky that current surveys don't cover well. Southern Hemisphere observations lag behind Northern Hemisphere coverage. High-inclination objects, coming in steeply above or below the ecliptic, are harder to detect because most surveys focus on the plane where most solar system objects orbit. And objects with low albedo, dark surfaces that don't reflect much sunlight, can slip through detection grids entirely unless they pass very close or happen to occult a background star. Atlas came in on a high-inclination trajectory. It's dark, at least darker than typical comets. And it came from interstellar space, a direction we weren't specifically watching because until recently interstellar visitors were theoretical curiosities, not practical concerns. We got lucky. We spotted it. But how many didn't we spot? How many objects, smaller, darker, quieter, passed through without triggering alarms? And how many are still on their way, invisible in the gaps between our survey fields, waiting to announce themselves only when they're close enough to be dangerous? This is the nightmare that keeps planetary defense experts awake. Not the known threats, those you can track, model, and potentially mitigate. It's the unknown threats, the objects you don't see coming because they're hidden in your blind spots, moving on trajectories you didn't anticipate, arriving at times and from directions your model said were unlikely. And if the Oort Cloud has structure, if it has filaments and streams and density enhancements that standard models ignore, then the number of unknown threats could be far higher than we've acknowledged. So we're left with questions. Is the Oort Cloud smooth or structured? Did Atlas pass through a dense region or empty space? Is there a filament, a stream, a concentrated population of objects now heading our way? And if so, when will they arrive, and what will they bring? We don't have answers, but we have the awareness that our ignorance is not benign. Blind spots hide dangers, and in space, what you don't see absolutely can hurt you. Part 11. This year's gravitational wave outlier. Could there be hidden compact objects passing through? Earlier this year, gravitational wave detectors picked up something they weren't expecting. A blip, microseconds long, gone before anyone could verify what caused it. Too short to fit the profile of colliding black holes, too faint to match neutron star mergers, too weird to dismiss as instrumental noise, but too brief to definitively classify as anything known. The event appeared in the data logs, got flagged by automated systems, sparked a flurry of internal emails among physicists, and then vanished into the archive of unexplained signals. Just another anomaly in a universe full of them. Except we're in 2025 now, and the list of anomalies is getting longer. Faster than it should. We're supposed to be getting better at understanding the cosmos, not more confused. Better instruments should mean fewer mysteries, not more. But gravitational wave astronomy, still in its infancy, keeps delivering surprises. Objects we didn't know existed. Processes we didn't predict. Signals that don't fit the templates we built based on what we thought was possible. So what could produce a microsecond gravitational wave burst? The leading candidates are exotic. Primordial black holes, remnants from the first fraction of a second after the Big Bang, far smaller than stellar mass black holes, maybe only a few times the mass of Earth, wandering through space undetected until they do something violent. Or cosmic string cusps, hypothetical defects in space-time left over from phase transitions in the early universe, producing sharp gravitational pulses when they whip around at relativistic speeds. Or maybe it's an instrumental glitch, a coincidence of noise patterns that looks like a signal but isn't. That's always the safest bet when you see something unprecedented. But here's the uncomfortable question. If compact, massive, nearly invisible bodies roam interstellar space, objects we can't see with telescopes because they don't emit light, don't reflect sunlight, and only reveal themselves through gravitational effects, then what happens when they pass through the Oort Cloud? A primordial black hole, even a small one, carries enormous density packed into a tiny volume. Its gravitational influence would be intense, localized, and brief. Any icy body that wandered too close would get yanked onto a new trajectory, possibly fragmented by tidal forces, or even captured into a temporary orbit before being flung away, and we'd never see the black hole itself. We'd only see the debris it left behind. This connects to the 3-eye Atlas debate in a way that should make us nervous, because if Atlas is unusual, if it's behaving in ways that don't quite fit standard comet models, maybe it's not the only unusual thing out there. Maybe interstellar space is more crowded, more dynamic, and more dangerous than we've assumed. We've been operating under the premise that the void between stars is mostly empty. A few atoms per cubic meter, some stray molecules, occasional clouds of gas and dust. But what if there are objects we're missing? Compact bodies that don't show up in surveys because they're dark, small, or just too weird to recognize? Atlas could be part of a larger class of interstellar wanderers, some visible, like comets with glowing comet, some invisible, like primordial black holes or rogue substellar objects. And if these things pass through the Oort cloud regularly, on timescales of thousands or millions of years, then the cloud isn't stable. It's being constantly perturbed, constantly stirred, with waves of debris kicked loose and sent inward at irregular intervals. We wouldn't see the pattern because our observational baseline is too short. A few decades of modern astronomy can't capture processes that unfold over millennia. The gravitational wave blip, if it's real, expands our sense of cosmic threat beyond objects we can see. Because electromagnetic signatures, light and radiation, are how we detect most dangers. Asteroids reflect sunlight. Comets glow when they outgas. Stars shine. But gravitational effects are harder to spot. They require sensitive instruments, careful analysis, and luck. A black hole passing through the Oort cloud wouldn't announce itself. It would just disturb orbits, break apart loose aggregates, and move on. And we'd only know it happened when the debris started arriving, years or decades later, with no obvious source. This is the nightmare scenario for planetary defense. Invisible perturbers, unknown objects that we can't track because we don't know they exist. Atlas, at least, is visible. We can photograph it, measure its spectrum, calculate its orbit. But what about the next intruder? What if it's smaller, darker, denser, and passes through undetected, leaving only a wake of disturbed material that shows up as a statistical anomaly in comet detections? How do you defend against something you can't see? The answer for now is that you can't. You watch for secondary effects, you monitor flux rates, track orbital distributions, and look for patterns that suggest external perturbations. It's indirect, statistical, and frustratingly slow, but it's all we have. Until we build better gravitational wave networks, until we can detect compact objects at greater distances, and with higher precision, we're flying partially blind. And that's terrifying when you consider what might be out there. Some physicists are pushing for expanded gravitational wave monitoring specifically to detect primordial black holes or other exotic compact objects in the solar system's vicinity. The idea is to create an early warning network, not for collisions but for close passes. Anything massive enough to perturb the Oort cloud should produce a detectable gravitational signature if it passes within a certain distance. The technology exists. The funding, as always, is the limiting factor. But the motivation is there, especially as we start to realize how little we know about the local cosmic environment. Let me be clear about the uncertainty here. The gravitational wave blip might be nothing, an instrumental artifact, a cosmic coincidence. There's no concrete evidence linking it to the Oort cloud, to Atlas, or to any specific object. But the fact that we detected it at all, that we're seeing signals we can't easily explain, should make us pay attention. Because the universe has a habit of surprising us. And surprises, in the context of planetary safety, are never welcome. We're expanding the threat model. Comets and asteroids are the traditional concerns, the objects we've built detection networks to find and track. But now we're adding dark comets, interstellar visitors, and potentially exotic compact objects to the list. Each one represents a different failure mode, a different way the solar system's stability could be disrupted, and each one requires different detection strategies, different response protocols, different ways of thinking about risk. Atlas might be the visible member of an invisible fleet, the one object bright enough, large enough, and active enough to catch our attention. While behind it, around it, maybe even ahead of it, other bodies move through the outer solar system undetected. Some might be natural, some might be stranger than we can imagine. And all of them, visible or not, pose questions we're only beginning to ask. The gravitational wave outlier is a reminder that we live in a cosmos we don't fully understand, and that our neighbourhood, the volume of space we call the solar system, is not as quiet or stable as we'd like to believe. Part 12. The 2025 Fast Radio Burst. Mystery, magnetic environments, precession, and what it means for weird bodies. Radio telescopes scanning the sky for transient events picked up another oddity this year. A fast radio burst, one of those intense, millisecond duration flashes of radio emission that nobody fully understands. But this one had a twist. Instead of the usual pattern, where repeating bursts come faster and faster, increasing in frequency as some mechanism winds up toward a climax, this burst showed the opposite behaviour. The intervals between pulses were getting longer, stretching out, as if whatever was producing them was slowing down, cooling off, or drifting away from the conditions that trigger emission. Fast. Radio bursts are already mysterious enough. We've been detecting them for less than 20 years, and despite hundreds of observations and dozens of theories, we still don't have a definitive explanation for what causes them. Magnetas, highly magnetized neutron stars, are the leading candidate. These objects have magnetic fields trillions of times stronger than Earth's, and when their crusts crack or their magnetospheres reorganize, they can release enormous bursts of energy in the radio spectrum. But not all fast radio bursts behave like magnetar flares. Some repeat, some don't. Some show frequency drift. Some show polarization changes. It's a zoo of phenomena masquerading as a single class of event. The 2025 burst with increasing temporal spacing doesn't fit the standard magnetar model. Magnetars should spin down gradually as they lose rotational energy, but the emission intervals shouldn't increase unless something external is changing. Maybe orbital precession, if the magnetar is in a binary system and its rotation axis is wobbling relative to its orbital plane. Maybe interaction with an external magnetic or plasma environment, something that modulates the emission mechanism, or maybe it's not a magnetar at all, maybe it's something else, something we haven't categorized yet, producing radio bursts through a process we don't understand. Why does this matter for 3I Atlas and the Oort Cloud scenario? Because it's another example of cosmic objects behaving in ways that defy our current models. We build theories based on what we observe, and then reality delivers something that doesn't fit. And when that happens repeatedly across different fields of astronomy, you start to wonder if the problem isn't the individual objects but our understanding of the underlying physics. Maybe the universe is more dynamic, more interactive, more prone to unexpected electromagnetic and gravitational effects than textbook models assume. If small interstellar bodies, or fragments from disrupted objects, can carry magnetic fields or generate plasma halos, then as they move through the outer solar system, they might leave behind transient electromagnetic signatures. Not strong enough to be easily detected from Earth, but strong enough to perturb charged dust, ionize molecules, or create temporary structures in the local plasma environment. These effects would complicate detection because they produce signals that don't match what we expect from passive, inert chunks of ice and rock. The fast radio burst example shows that nature can produce intense, localized electromagnetic phenomena in unexpected places. If a magnetar can crack its crust and release a burst visible across billions of light years, what might a smaller, closer stranger object do? Maybe nothing. Maybe these effects require extreme conditions that only exist in neutron stars and black holes. But maybe not. Maybe there are intermediate cases, objects with modest magnetic fields, but unusual geometries or rotation states that can produce localized bursts, transient emissions or other phenomena that we're not specifically looking for. This broadens the diagnostic toolkit for identifying unusual objects. Instead of relying solely on optical observations, looking for reflected sunlight or emission lines from outgassing, we should also be monitoring radio frequencies, X-ray bands, and other wavelengths where electromagnetic activity might reveal itself. Atlas, if it carries a magnetic field or generates a plasma halo, might be detectable through radio emissions that standard comet surveys wouldn't catch. And if Atlas is detectable this way, then so are other objects in its class. Some researchers are proposing multi-wavelength monitoring campaigns specifically for interstellar visitors and unusual near-Earth objects. The idea is to look at each new detection not just as a trajectory problem, where you calculate orbits and assess collision risk, but as a physics problem, where you probe for unexpected emissions, field structures, or interactions with the local environment. This is harder, more expensive, and requires coordination across multiple observatories and instrument types. But it's the only way to catch phenomena that don't announce themselves through traditional channels. The fast radio burst mystery also reinforces a broader point. Our cosmic backyard is more complex than comets, asteroids, and rubble piles. Objects can carry magnetic fields. They can interact with plasma environments. They can produce emissions across the electromagnetic spectrum. They can fragment, merge, accrete material, or shed debris in ways that don't fit simple gravitational models. And when they do, they challenge our ability to detect, track, and assess them. Atlas might be just the tip of the iceberg, the most visible example of a class of objects that includes many more members, most of which we haven't detected yet. Some might be larger, some might be smaller, some might be brighter, and some completely dark. But all of them, to varying degrees, might exhibit behaviours that complicate our standard detection and tracking methods. And that's a problem, because planetary defence relies on knowing what's out there, where it's going, and how dangerous it is. If objects can hide in plain sight, either by being dark, by producing confusing emissions, or by behaving in ways our algorithms don't recognise, then our risk assessments are incomplete. The increasing temporal spacing in the fast radio burst could be a clue to understanding precession, orbital dynamics, or environmental interactions in extreme magnetic systems. Or it could be a fluke, an instrumental artifact, a one-off event that never repeats and never gets explained. But the fact that we're seeing it at all, that the universe keeps delivering surprises even as our instruments improve, suggests that we're still in the early stages of understanding cosmic phenomena, and that humility, that recognition of how much we don't know, should inform how we think about objects like Atlas. Because if we're wrong about fast radio bursts, if our models are incomplete and the universe is stranger than we thought, then maybe we're also wrong about comets, about Oort Cloud dynamics, about what happens when an interstellar visitor passes through, and if we're wrong, then the risk assessments we've made, the reassurances we've given, might be based on incomplete physics, which means the danger could be greater than we've acknowledged. So we watch, we listen, we build better instruments and ask better questions, and we accept that the cosmos will continue to surprise us, whether we're ready or not. Part 13. The AI discovered rogue planet with a fragmented ring, a new class of interstellar troublemakers. Machine learning changed astronomy this year, not in a subtle way but dramatically, by finding objects that human observers would have missed. Algorithms trained on transit data from TESS and astrometric measurements from Euclid flagged an anomaly that didn't fit any existing catalogue. An object moving through interstellar space with no parent star, no obvious gravitational anchor, just drifting through the void. When follow-up observations confirmed the detection, astronomers found something unexpected. A rogue planet. And not just any rogue planet. This one had a ring system, fragmented, asymmetric, falling apart as it tumbled through space. Rogue planets are not new. We've known for years that planets can be ejected from their home star systems through gravitational interactions, close encounters with other planets, or stellar flybys. Once ejected, they drift through interstellar space indefinitely, frozen, dark, invisible, except through direct imaging or microlensing events. Estimates suggest there could be billions of rogue planets in the galaxy, outnumbering stars. But we rarely detect them because they're so faint and so far away. This one is different. It's close, cosmically speaking, only a few hundred light years away, and it's moving fast. The ring system suggests it was violently disrupted, possibly torn apart by tidal forces during ejection from its original system. The rings are chaotic, not the neat stable structures you see around Saturn or Jupiter, but debris clouds, fragments of moons or co-orbital material, slowly spreading out as the planet tumbles through space. It's a graveyard, a planetary corpse dragging its own debris field. Why does this matter for the 3I Atlas scenario? Because it shows that interstellar objects are not limited to tiny comets or asteroids. Some are massive, planetary scale. And if they pass through our solar system, or even near the Oort Cloud, the gravitational disturbance would be enormous. A Jupiter-mass rogue planet passing within a few thousand astronomical units of the Sun could perturb thousands of Oort Cloud objects, sending them on new trajectories, some inward toward the inner solar system, some outward into interstellar space. And we might not detect the rogue planet itself, especially if it's dark, far away, and moving perpendicular to the plane of the solar system. Atlas, in this context, starts to look less like a freak event and more like part of a broader class. Interstellar visitors come in many forms: small comets, large comets, asteroids, fragments, and apparently rogue planets with ring systems. Each one represents a different level of threat, a different mechanism of disruption. Small objects cause local perturbations, large objects cause systemic disturbances, and if we're unlucky, a massive intruder could trigger a cascade, a flood of inbound debris that lasts for centuries. The fragmented ring system is particularly interesting because it implies the rogue planet isn't travelling alone. It's dragging debris, moons maybe, or fragments of moons, trapped in unstable orbits around the planet as it drifts through space. If such an object passed through the Oort Cloud, the ring material could interact with local bodies, scattering them, fragmenting them, or even capturing some into temporary orbits. The result would be a mess. A chaotic mixing of populations with objects on wildly different trajectories, some fast, some slow, some inbound, some outbound, all stirred up by the passage of the intruder. This parallels what we're speculating about Atlas. Maybe it's not alone. Maybe it's part of a stream, a trail of fragments following a common trajectory. Or maybe it passed through a dense region and kicked loose material that's now trailing behind. The rogue planet example shows that such scenarios are physically plausible. Objects can travel with companions, debris fields, or ring systems, and when they pass through our neighbourhood, they don't just perturb orbits, they redistribute material, fragment objects, and create new populations of debris that we have to track and assess. Some researchers are now proposing that we expand planetary defence to include rogue planet detection. Not because rogue planets themselves pose an immediate collision risk, they're too large to sneak up on us and too massive to deflect, but because they can disturb the Oort Cloud and trigger secondary effects. A rogue planet passing through 1,000 astronomical units away wouldn't threaten Earth directly, but it could send thousands of comets and fragments our way over the following centuries. That's a long-term threat, one that requires monitoring on generational timescales. The AI discovery aspect is also significant. Machine learning algorithms are better than humans at finding patterns in massive datasets, at spotting anomalies that don't fit expectations. As we deploy more automated surveys, more sky-scanning telescopes, and more data processing pipelines, we're going to find more weird objects. Some will be rogue planets, some will be interstellar comets, some will be things we don't have names for yet. And each new discovery will refine our understanding of what's out there, how common these objects are, and what risks they pose. The fragmented ring system also raises questions about stability. If the rings are falling apart, where's the debris going? Is it spreading out into a diffuse cloud, or is it concentrating into streams that follow the planet's trajectory? If the latter, then anyone encountering this rogue planet in the future might not just see the planet itself, but a debris field extending thousands or millions of kilometers ahead and behind. A cosmic minefield, invisible until you're already in it. Atlas, if it's analogous, might be the bright nucleus of a much larger structure, the visible part of a debris field that extends far beyond what we can currently detect. And if that's the case, then tracking Atlas alone isn't enough. We need to map the entire field, identify all the fragments, and assess whether any of them pose a threat. That's a monumental task, one that current detection systems aren't designed for. But it's necessary if we want a complete picture of the risk. The rogue planet discovery expands the threat horizon. We're no longer just worried about comets and asteroids, the traditional near-Earth hazards. Now we're adding rogue planets, ring system debris, interstellar fragments, and potentially other exotic objects to the list. Each one requires different detection methods, different tracking strategies, and different risk models. And all of them, in aggregate, paint a picture of a solar system that's more dynamic, more interactive, and more vulnerable than we once believed. Atlas might be the herald, the first visible sign of a broader wave, and if that's true, then the discoveries to come will reshape our understanding of cosmic hazards, for better or worse. Part 14, The Laboratory, Microgravity Well. Experiment. Could exotic physics change how we see gravity and debris interaction? Physicists working with precision interferometers in a laboratory this year reported something strange, a deviation. Small, barely outside the noise, but persistent enough to trigger internal reviews and prompt follow-up experiments. They were testing gravitational behavior at small scales, looking for deviations from Newtonian mechanics or general relativity, the kind of experiments that usually confirm existing theory, but occasionally, very rarely, hint at something new. And this time, the results didn't quite match predictions. There were transient anomalies, brief moments where the measured curvature or gravitational gradient was slightly off from what the equation said it should be. This is not confirmed, it's not peer-reviewed, it's the kind of result that could evaporate under scrutiny, explained away by systematic errors, calibration issues, or environmental noise. But it's also the kind of result that makes theorists uncomfortable, because if it's real, if there are genuine deviations from standard gravitational theory at small scales, then everything we think we know about how objects interact might be wrong, or at least incomplete. Why does this matter for 3I Atlas and the Oort Cloud? Because our risk models, our predictions about how debris moves and how objects respond to perturbations, are all built on standard physics. Newtonian gravity for most calculations, general relativity when precision matters, and electromagnetic theory for charge-particle interactions. If there are effects we're missing, if gravity or field interactions behave differently under certain conditions, then our predictions could be systematically biased. We might be underestimating how quickly material can be perturbed, how efficiently it can be accelerated, or how tightly it can be corralled into streams. Imagine if localized field configurations, combinations of gravitational and electromagnetic influences, can create temporary wells or distortions that amplify perturbation effects. An object like Atlas, if it carries unusual field geometry, or interacts with the local environment in unexpected ways, might not just nudge nearby bodies, it might trap them, accelerate them, or funnel them into coherent streams far more efficiently than standard models predict. And if that's possible, then the timeline collapses. Objects don't take millennia to arrive, they take decades, maybe years. This is wildly speculative. We're talking about physics that hasn't been confirmed, applied to scenarios we can barely model, to explain effects that might not even be real. But speculation has value when it expands the possibility space, when it forces us to question assumptions we've been taking for granted. Because if the microgravity well experiments are real, if there are genuine anomalies in how gravity behaves under certain conditions, then we need to revisit every calculation, every simulation, every risk assessment we've made for near-Earth hazards. The laboratory results, if they hold up, might indicate modifications to gravity at short ranges or under high curvature conditions. That wouldn't affect planetary orbits, where distances are large and curvatures are modest. But it could affect small bodies, where close encounters and tight orbital maneuvers create localized regions of intense gravitational gradient. An object passing through the Oort Cloud, skimming close to thousands of small bodies, might generate transient field effects that standard theory doesn't account for. And those effects could change outcomes dramatically. This introduces a wild card into the Atlas scenario. Maybe it's not just about mass, velocity, and density. Maybe there are field effects, exotic interactions, or unknown physics playing a role, and if that's true, then even a relatively small object could produce disproportionate disruption if it happens to hit the right conditions, the right field geometry, the right local environment. Connecting. This to Atlas requires several leaps of speculation. We'd need to assume the laboratory results are real and reproducible. We'd need to show that the same effects occur at astronomical scales, not just in tabletop experiments. We'd need to demonstrate that Atlas or objects like it can generate the necessary conditions, and we'd need to explain why we haven't seen clear evidence of such effects in other comets or asteroids. That's a tall order, but it's not impossible, The narrative payoff here is heightened mystery. If unknown physics is in play, then predicting outcomes becomes even harder. Standard models might give us ballpark estimates, but the real behavior could deviate significantly. And that uncertainty, that acknowledgement that we might be missing something fundamental, adds tension to the story. Because if we don't fully understand the physics, how can we be confident in our risk assessments? How do we know that Atlas isn't a more significant threat than we've calculated? The laboratory experiment, whether it pans out or not, serves a useful function in the broader narrative. It reminds us that physics is not complete, that we're still learning, that anomalies, when they appear, deserve attention even if they turn out to be measurement errors. Because occasionally, very occasionally, anomalies are real. And when they are, they change everything. For Atlas, the implication is simple. If exotic physics is at play, then the Herder hypothesis, the idea that Atlas is dragging or corralling debris, becomes more plausible. Because you don't need to invoke enormous mass or sustained electromagnetic fields if field geometry alone can amplify perturbation effects. A modest field, under the right conditions, could produce outsized results. This is the kind of speculation that makes mainstream scientists groan. But it's also the kind of speculation that keeps the door open to unexpected discoveries, and in the context of a what-if documentary, it's gold. It lets you explore possibilities beyond standard models, entertain exotic scenarios, and leave the audience with a sense of wonder and unease. Because if we're wrong about gravity, if there are effects we haven't discovered yet, then the universe is stranger and more dangerous than we thought. An Atlas, this glowing visitor from beyond, might be more than just a comet. It might be a messenger of unknown physics, a harbinger of surprises yet to come. Part 15. The AI Hazard Forecasting Platform that flagged 2025 as an outlier year. Is the solar system entering a period of increased dynamical flux? Somewhere in a server room, an algorithm flagged this year as unusual. Not catastrophically so, not apocalypse imminent, but statistically anomalous in ways that deserve attention. The system, a multi-observatory artificial intelligence-powered early warning platform, combines data from sky surveys, infrared observations, trajectory catalogues, and historical detection records. It's designed to look for patterns, not just individual threats. And this year, 2025, the pattern looks different. More high-inclination objects than expected, more long-period entries, more low-albedo near-Earth objects showing up in surveys, a surge that's harder to explain away as detection bias or improved instrumentation. This kind of system represents the next evolution in planetary defense. We've moved beyond simply cataloguing known objects and calculating collision probabilities. Now we're trying to detect anomalies in the background flux, changes in the rate at which new objects enter the inner solar system, variations in orbital element distributions that might signal an external perturbation. It's pattern recognition on a cosmic scale, using machine learning to spot deviations that human analysts might miss. So what does it mean when the system flags a year as anomalous? It means the number of detections, or the characteristics of those detections, falls outside the expected range based on historical trends. Maybe there are more objects coming in from high inclinations than statistical models predict. Maybe the size distribution is skewed towards smaller, darker bodies. Maybe the timing, the spacing between detections, shows clustering rather than random distribution. Any of these could indicate something real, something beyond normal variation. The flag doesn't tell you what caused the anomaly, it just says something changed. And now humans have to figure out why. Is it instrumental? Have survey strategies shifted, covering more of the sky or using different filters that preferentially detect certain types of objects? Is it statistical noise, a random fluctuation that looks significant but will regress to the mean next year? Or is it real? Is the inner solar system genuinely experiencing increased flux? And if so, what triggered it? 3i Atlas is the obvious candidate. Its arrival coincides with the anomaly, but correlation isn't causation. Maybe Atlas is unrelated, and the real cause is something else. A previous perturbation, years or decades ago, finally manifesting as increased flux. Or maybe multiple factors are converging. Galactic tides, stellar flybys, and interstellar visitors all contributing to a temporary uptick in Oort Cloud destabilization. The solar system might be entering a disturbance era, a period where multiple external influences combine to increase the rate at which long-period comets and dark objects enter the inner system. If that's true, then Atlas isn't the source. It's a marker, a visible signal of a broader process already underway. And the real question is how long the disturbance era will last. Years? Decades? Centuries? And how severe will it get? Will the flux continue to rise, or will it plateau and then decline as the disturbed material clears out? We don't know because we've never witnessed such an event in the modern era. Our observational baseline is too short to capture long-period variations in Oort Cloud dynamics. The AI system can help by monitoring trends in real time, updating predictions as new data comes in, and flagging deviations early enough for follow-up observations. If the anomaly persists, if next year and the year after continue to show elevated flux, that strengthens the case for a real disturbance. If it fades, then maybe it was just a blip, a statistical quirk amplified by improved detection. Either way, the system provides a framework for tracking changes over time, for distinguishing signal from noise, and for making informed decisions about resource allocation and risk mitigation. The counter-arguments are predictable. Detection biases could explain everything. More surveys mean more detections. Better algorithms catch objects that would have been missed a decade ago. Expanding sky coverage reaches regions previously undersampled. All of this increases the apparent flux without any real change in the underlying population. You'd expect an upward trend as capabilities improve. The question is whether the observed trend exceeds what improved capabilities alone would predict. Statisticians can model expected detection rates based on known improvements in instrumentation, survey coverage, and data processing. If the observed rate falls within the confidence intervals of those models, then there's no anomaly. But if it falls outside, significantly outside, then something else is happening. And that's when you start looking for physical explanations, perturbations, disruptions, external influences, things that change the actual flux, not just our ability to detect it. The AI platform is still being calibrated, still learning what's normal and what's not. But the fact that it flagged 2025 at all is noteworthy. Because if the system is working as intended, if it's genuinely detecting patterns beyond random variation, then we might be at the beginning of something significant. A new phase in the solar system's evolution. A period where the Oort Cloud is more active, more disrupted, sending more material inward at a faster rate than the long-term average. Atlas, in this scenario, is the first visible signal. The comet that made us look harder, that triggered follow-up observations, that prompted development of better monitoring systems. And maybe, just maybe, it's the herald of a wave. A pulse of inbound objects that will unfold over the coming decades, challenging our detection networks, testing our response capabilities, and forcing us to rethink what we thought we knew about the stability of our cosmic neighborhood. The open-ended question remains, is our solar system entering a new era of heightened risk and flux? And if so, what does that mean for Earth, for our satellites, our infrastructure, our long-term survival as a species dependent on a fragile biosphere? We don't have answers yet, but we have the question, and we have the tools, the algorithms, the telescopes, and the human ingenuity to start looking for answers. The universe is not static. It changes, evolves, surprises us. And sometimes, those surprises arrive on hyperbolic trajectories, glowing in the sunlight, dragging invisible companions behind them. Atlas passed through, but its wake, if it exists, is still arriving, and we're only beginning to understand what that might mean.